this video we will discuss about the Lewis bond theory, electronegativity, and bond polarity, because at this point we have discussed everything that is to periodic properties, and the periodic properties allows us to understand why the elements behave the way they do. And one of the main things that we need to remember from the periodic properties is that basically all elements want to be a noble gas. Okay, and that has to do with the electrons. Now, all noble gases have 8 electrons in the last shell, and every single element in the periodic table wants to do the same. And the way they can do that, because they are not noble gases, the noble gases already have those 8 electrons, but the way the other elements have to achieve that goal is to forming bonds. So the Lewis bond theory is the first step into understanding how the atoms connect the way they do. So before we get there, let's explore a little bit of how the atoms connect to each other, how those bonds that form between atoms occur. So the reason they do that, why they form bonds, is to lower the potential energy. They want stability, and that stability is related to those 8 electrons. Remember, the noble gases are really stable, they are very unreactive, and that has been associated with the 8 electrons in the last shell. So they form bonds because they acquire those 8 electrons in the last shell most of the time, and in doing that they gain stability, which means the potential energy goes down. So there are two main types of bonding. We have ionic bonding and covalent bonding, and the main difference between those two is how, or at this point, mostly who forms ionic or covalent bonds. So the first one, if you have metals and non-metals, and remember, you already know how to explore that in the periodic table, in which side is the non-metals and where are the non-metals. Metals and non-metals, sorry. So whenever you have a metal and a non-metal in the same compound, usually that is an ionic compound, ionic bond. And the main feature of this ionic bond is that the electrons are being transferred. There is one element that will completely lose electrons. Sounds familiar? And there is another element that will completely gain electrons. So there is a transfer, a full transfer of the electrons. Now, when you have non-metals and the non-metals react with each other, then they tend to form a covalent bond. And in that case, that bond occurs because the electrons are being shared, not completely transferred. So think in terms of that in the ionic bond, there is a transfer of ownership of those electrons, but in a covalent bond, there is no such a transfer, and each one of the elements still keep their electrons. Okay, so if we look into more detail, the ionic bond usually is formed between elements that have low ionization energies. And sorry, let's put this ionization energies, which correspond to metals. The metals are usually low in ionization energies, and with elements that have high electron affinities. Remember, the ionization energy is the tendency to lose electrons. The electron affinity is the tendency to gain electrons. So you combine a metal that wants to lose electrons with a non-metal that wants to gain the electrons, and everyone is happy. Okay, you have a transfer of electrons. In a covalent bond, you have elements that both will have high electron affinities. They really want those electrons. So think in terms of a competition here. Those two non-metals want to keep the electrons, but nobody really wins. So those electrons are sort of in the middle. So that's what we call sharing of electrons. There is a third type of bond that we will not go into too much detail there, but it's the metallic bond. And the metallic bond is, if we have the covalent bond with high electron affinities, the metallic bond occurs between elements that with low ionization energies. Again, this is ionization energy. So the result there is that those electrons are delocalized. What does that mean is that, and if we take a look at all of these bonds, during the ionic bond, the electrons that are part of that bond, they are all interacting with one of the nuclei. Remember, it's total transfer, so one element completely loses those electrons, and those electrons are spending time with the other element. In the covalent bond, those electrons get to interact with both nuclei. Remember, think of those two atoms. The electrons are in the middle, but those electrons have the capacity to interact with both of those nuclei. In the metallic bond, however, think of, this is what they call, you may read this in the book, sea of electrons, because those electrons are really free to move around that network of nuclei. So they are not attached to any single atom. I mean, the initiation energy is so low that those electrons are free to move around as they please. Okay, so they are not bound to just one nucleus, but to the entire network of nuclei. So looking at the ionic bond, the way this bond forms is because you're forming ions. The cation is the element that is losing those electrons, and then you have the anions. Those are the ones that are gaining those electrons. Okay, once again, metals have low ionization energies, non-metals have large electron affinities, and by large we mean really negative electron affinities, meaning high affinity for those electrons. Okay, so that ionic bond forms because those opposite charges attract to each other. So think in terms of, you have a positively charged particle, that's your cation, and a negatively charged particle, that's your anion. So those two particles are held together because of that attraction between opposite charges. In the covalent bond, however, because the non-metals have high ionization energies, it's kind of difficult to remove the electron. I mean, you can still remove the electron, it's just that it requires so much energy that for practical purposes it doesn't happen. So that sharing of electrons is what we call the covalent bond, and because you are with those electrons in the middle, then those atoms are held together because of the attraction of those electrons. Remember, think of each atom pulling on those electrons. So because they are pulling at the same time, then they get to stay connected. So we call covalent compounds any substances which only have covalent bonds. And another term that we use to those compounds is molecular compounds. Remember, molecular compounds would be all covalent bonds. Ionic compounds require the presence of ionic bonds. Sometimes you may have ionic compounds which have some covalent bonds. Remember, the polyatomic ions, it's an ion, it's going to participate in an ionic bond, but that polyatomic ion inside has covalent bonds. One term that we're gonna be using a lot in during the semester is the concept of lone pair. Okay, lone pair are electrons that are not being shared. Okay, so we also call it unshared electrons. So the electrons that are participating in a bond, you call that shared electrons or bonding electrons. Let's call these bonding electrons. Are the electrons in a bond, and we are assuming it's a covalent bond for that matter. Okay, so we have bonding electrons and you have non-bonding electrons. The non-bonding electrons, those electrons not participating in a covalent bond, is what we call lone pairs. Now the concept of electronegativity, this is related to a bond. Okay, so a bond is formed between two atoms. Okay, it's similar in terms of you can relate this to periodic properties, but all the periodic properties that we have discussed so far has to do with one atom. But in electronegativity, it's implying that there are at least two atoms there because it refers to a bond. So in this case, electronegativity refers to the ability of an atom to attract electrons to itself. But those electrons are special. Those electrons are bonding electrons. So it's the ability of an atom to attract bonding electrons. Okay, so that atom has to be participating in a bond. Now, that's kind of similar to electron affinity, but electron affinity, even though it's also attraction of electrons by an atom, it refers to an isolated atom. It's the atom by itself, and it's attracting electrons from anywhere. So those electrons are not restricted to any particular situation. Electronegativity restricts those electrons to be part of a bond, so there is the presence of another atom there, and the electronegativity is how much that atom or one of those atoms can pull those electrons to themselves. Okay. Now, this electronegativity is really important because it will tell us what type of bond is formed. So we have ionic, and it has to do, all of this has to do with difference in electronegativity. So a difference in electronegativity gives you different abilities to pull those electrons toward yourself. So an ionic bond forms when the difference in electronegativity is really large. A pure covalent bond forms when the difference in electronegativity is practically zero. And the polar covalent bond is when there is it's somewhere in between. So we're gonna explore that into more detail. Okay, and this sounds familiar, or this looks familiar. Let me rephrase that, because it's a periodic table with values of electronegativity and the word trend in pretty much the same way that we've been using trends in atomic size, in ionic radii, ionization energy, and such. So there are certain values here, and pretty much the same as with the other periodic properties. You don't really have to memorize those numbers. You just need to know how the electronegativity changes as you move through the periodic table. So what you see here is that, for example, if you go left to right, and let's say electronegativity increases if you go left to right in the periodic table. And what you also see here is that the electronegativity also increases up a group. Okay, so when it comes to remembering, first of all, you have to remember how the electronegativity changes with the periodic table. Particularly, you should be very comfortable with exploring electronegativity in the second period elements, from boron to fluorine, and how the electronegativity changes with the halogens in particular. So remember halogens, and remember second period elements. Okay, and if you were to memorize anything out of the periodic table, is that you see this element here. Fluorine is the most electronegative atom in the periodic table. What that really means is that when you are pulling electrons, fluorine always wins. Okay, there is nothing stronger than fluorine in attracting electrons. Okay, that's the main thing to remember out of this periodic table. Okay, so this is important because when we refer to equal and unequal sharing, we are trying to distinguish between a pure covalent and a polar covalent bond. So what this really means is that taking a look at the chlorine molecule, chlorine is the same atom. If you are looking at the value of electronegativity, well, they have the same value. You can see this from the point of view of that each chlorine atom is equally strong into attracting those electrons. So those electrons are going to be right down the middle of these two atoms. Okay, this is what we call a nonpolar covalent bond or pure covalent bond. And what that means is that those electrons are being shared, yes, but because they are being equally shared, then they get to spend equal amount of time around each nuclei. So let's say 50% of the time those electrons are around one of the chlorine, 50% of the time they are around the other chlorine. Now, unequal sharing refers to when you have different strength in electronegativity. So in this case, chlorine is more electronegative than hydrogen, so it does a better job at pulling those electrons toward itself, and that's what we call a polar covalent bond. And the reason we call this a polar covalent bond is because those electrons being more attracted towards the chlorine, those electrons spend more time around the chlorine atom, which means that the chlorine atom develops a partial, these are partial charges, not fully developed charges. It's not chlorine -1 and hydrogen +1. It's a partial positive charge in the hydrogen and a partial negative charge in the chlorine. And what this really means is that this partial negative charge means there is a higher electron density around the chlorine atom. And of course, if there is a higher electron density around the chlorine atom, there is a lower electron density around hydrogen. Okay, you are forming here, this is having that positive partial charge and the negative partial charge there originates a dipole. And because you have a dipole, is that you call this a polar covalent bond. Now there are cutoff if we are looking at the values of electronegativity, saying let me tell you, you might not really have to worry too much about these values. However, for this class, for Dr. A here, we're gonna use these cutoff values. Okay, they differ among instructors, they differ among books, but to keep things simple, we're gonna refer to this cutoff. So let's say if the difference in electronegativity, okay, this value here, if the difference in electronegativity is less than 0.4, then you have a covalent bond, or let's say a pure covalent bond, or simply put, nonpolar. All of these are kind of equivalent. Now, if the difference is larger than 0.4 but smaller than 2.0, then you have a polar bond. And if it's larger than 2.0, then it's an ionic bond. Okay, larger than 2.0, it's ionic. Okay, so that's how you can explain, based on electronegativity, what are the different types of bonds that you can form. Now, these polar covalent bonds, remember, partial negative charge, partial positive charge, you are creating a dipole. Think in terms of you are creating a magnet. And what's special about this magnet is that in the absence of an electrical field, they are just randomly moving around. But if you apply an electrical field, and let's call this a difference of potential here, then those dipoles will align with that electrical field. So the positive side is pointing towards the negative plate, and the negative side of that dipole will be pointing towards the positive side of that plate. Okay, that's basically what the observed behavior for this type of molecules is. We can also quantify that, not that you have to worry too much about it, but you can assign a number to this. Okay, this is what we call dipole moment. And the dipole moment, basically what it tells you is how polar a bond is. Okay, so there are changes in polarity, and that change in polarity depends on the difference in electronegativity. Okay, so if the difference in electronegativity increases, then the polarity of the bond also increases. Okay, to what point? Well, towards the point in which you obtain a ionic bond. For practical purposes in this class, we can explain the concept of polarity and the increasing polarity of a bond basically in terms of electronegativity. However, for using dipole moment to describe polarity, all we need to know is that if you have a dipole moment equal to 0, that's equal to a non-polar bond, and if you have a dipole moment different from 0, I don't care if it's 0.1, 0.2, 0.3, 3, doesn't really matter, that is a polar bond or polar molecule. Okay, so this is basically all we need to handle dipole moments, okay, whether it's non-polar or polar bond. Now in this case we have several situations, and we are to determine whether it's an ionic, a polar covalent, or a covalent bond. So here we have metal plus non-metal. Here you go straight to ionic. There is nothing to think here. Now carbon and oxygen. These are two non-metals. Okay? And as such, you are forming a covalent bond. And in this case, when you have to determine whether it's a polar or non-polar, carbon is less electronegative than oxygen, and in this case, you can use values. This is 2.5, this is 3.5. So the difference here, the difference in electronegativity is 1. So this is a polar covalent bond. And between nitrogen and oxygen, well, nitrogen is 3 and oxygen is 3.5. These are also non-metals. It's a covalent bond, and the difference in electronegativity is 0.5. So you are very, very close to the cutoff. So this is a covalent bond. You can even say this is slightly polar. Okay, and you can also say that the carbon-oxygen bond is more polar than the nitrogen-oxygen bond. Okay, you can even say this even if you don't have these values. That's just based on the periodic table, because if you look at those three, you have carbon, nitrogen, and oxygen. Nitrogen and oxygen are basically next to each other, and there are two spaces between carbon and oxygen, and remember, electronegativity increases in that direction. Therefore, oxygen, out of those three, oxygen is the most electronegative, carbon is the least electronegative. That's why the carbon-oxygen bond is more polar than the nitrogen-oxygen bond. Okay? Now, finally, we made it to the Lewis theory of bonding, which is basically a way that we have to explain how this bond forms. And not much to remember out of this, except that it was Lewis quite a few years ago. And here, this is the first step to understand or to draw Lewis structures, and basically we're going to be able to determine how the atoms are connected just based on this theory of bonding. Okay, and with this, one of the things that we're going to do later on is determine what the shape of the molecule is, what the polarity of the molecule is, and this is all the foundation that we need to explain that. An important thing to remember here are the valence electrons, and one thing that I want you to keep in mind is that we're going to limit our discussion to main groups because they are so much easier to work with. And for main groups, the valence electrons are in the last shell. And I'm making this distinction because the transition metals, sometimes the transition metals, you can consider the d electrons part of the valence electrons, and that complicates things more than we need to. So the point here is that if you take a look at the groups here, each one of these groups are associated with a particular number of valence electrons. So group 1 and group 2 are the easiest one. You have 1 valence electron and 2 valence electrons for each one of these groups. And from 13 to 18, then you have 3 to 8. So the easiest way to remember this is that if you have your group number, if it's 1 or 2, you have 1 or 2 valence electrons. And if you are from 13 to 18, all you have to do is to subtract 10 from that, and that gives you the number of valence electrons. So you don't have to worry about doing electron configurations anymore. If you just need the valence electrons, and those are the ones responsible for reactivity, all you have to do, if you are in a group higher than 10, you just take 10 out of that group, and that will give you the number of valence electrons. So that's the shortcut. And to work with Lewis dot symbols, basically you just take the element symbol and you put as many dots around that symbol as valence electrons that element has. So lithium, sodium, potassium is just one valence electron. That's just going to be one dot around the symbol. The noble gases, here neon, 8 electrons, 8 dots around the element symbol. So these are the dot symbols for each one of those elements, and those are useful because now we can explain how the bond forms. So in this case we have lithium fluoride. Lithium is 1s2 2s1, and fluorine is 1s2 2s2 2p5. There is a total transfer, so this electron goes completely to fluorine, and then lithium ends up with a 1s2 configuration, that's helium, and fluorine ends up with a 1s2 2s2 2p6, which is neon. Okay, remember, by transferring those electrons they acquire noble gas configuration. So another way we can see this is that we have lithium with that electron in the last shell. Lithium is losing that electron. Fluorine is gaining that electron, completing 8 in the last shell. So basically, here is your positively charged particle, here is your negatively charged particle, and those two are held together because of that electrostatic attraction. So if we take this example, now lithium and fluorine was easy because it's just one electron involved. But here you can see that we have a metal with 2 valence electrons and non-metal with 5 valence electrons. So the metal wants to lose those 2 electrons. The non-metal wants to complete 8, so it needs 3 more electrons. So these electrons will go here. But as we do that, then yes, now this has 7 electrons, and the metal got rid of its 2 electrons, but this non-metal is still not happy. So you need to provide more electrons, and that's why you add more of this. So now this electron goes here. This now has 8, and then you have 1, 2, and 3 more electrons here that will go to this guy, and now everyone is happy. Okay, and simply put, you have your negatively charged particle here, you have your positively charged particle here. They are being held together because of that electrostatic attraction. Okay, and our shortcut, and now you realize why you exchange charges when we were doing nomenclature. So this is a simplified version of what we're seeing here, but this is how Lewis explained how the ionic bond forms. Okay, so this is it for now. When we start doing Lewis structure, then we will go into more detail with the covalent bond, but this is it for now.